Okay, UALR final exam review for college algebra, problem number 35. The Game Commission introduces 100 deer into newly acquired state game lands. Population N of the herd is modeled by this function here, where T is greater than or equal to 0. T is the time in years. Use a graphing utility, remember that means calculator, to graph this model. All right, look at our scales here. We're going to look at both of these, but we're going to put this function in the calculator first. You have a newer operating system on your calculators, but this one I'm going to have to make sure and put the numerator in parentheses and the denominator in parentheses. So I've got 20 times 5 plus 3x. Remember, you can't use t on the calculator. That's the numerator in parentheses divided by the denominator in parentheses 1 plus 0.04x. And then I'm going to go to my window. It looks like, let's look at these. Two of these graphs have x from 0 to 200 and y from 0 to 120. So I'm going to set the window up like that. 0 to 200 and 0 to 120. See if we can see the graph. I do not see that graph in there. So we are going to try this one. Looks like 0 to 170 on the x-axis and from 0 to 1420 or 1450, something like that. So we'll set the window there. 0 to, we'll just leave it 0 to 2, well, 0 to 170. Then 0 to about 1450. A graph. That looks like that one. It's definitely not this one. And none of the others, so it looks like this is the graph. Well, I tried to circle it. You get the idea, right? Now it's asking us to find the populations when t equals 2, 12, and 27. Well, the easiest thing to do, since we have it in a calculator in the y equals, is to go to the table, 2, 12, and 27, right? So let me check and make sure that my table's set up here. It's good. So we're going to go second graph to get the table, and we'll go to t equals 2. So 203.7. If we're talking about a deer population, we can't have 203.7 deer. So you're either going to put 203 or 204. I'm going to put 204. We'll go to 12. 554. Or we go to, it was 27. About 827. Now it says, what is the limiting size of the deer herd as time increases? Well, we can kind of figure that out if we will just keep going down here. If you notice on the graph, we looked at the graph, it kind of leveled off. It never gets flat, but it gets lower and lower and lower. So we're going to go and see. We should come to a point. You could trace the graph also and watch the y values. Oh, let's see here. We should get to a point where it gets really, really, really close. Still growing. Goodness gracious. I thought we'd be growing by now. Let's look at it a different way. This is going to be the horizontal asymptote of the function. So if we look at this, we have a first degree polynomial on top, a first degree polynomial on the bottom. If we distribute that 20, we would get 100, this with pen, plus 60t on top, and we have 0.04t plus 1 on the bottom. The horizontal asymptote, like we talked about in the last problem, is the leading coefficient over leading coefficient because the degrees are the same. So the horizontal asymptote, that's the value that the function is going to approach as we go to infinity, but it's never going to reach, is going to be the line, y equals 60 divided by 0.04, leading coefficient over leading coefficient. This will be a little easier in tracing. I thought we'd be able to get to it quicker. But let's get second quit. Let's do 60 divided by 0.04. So 1,500 is what they're looking for the limiting factor. We call that the carrying capacity, right? When we did this. And that's how you do number 35. Oops. Well, goodness gracious. 35.